In this lecture, we're going to learn how to construct a confidence interval for a population proportion and a confidence interval for a standard deviation for a population. So we're going to start with section 8.3 first. That section starts on page 389. So it's about the confidence intervals for population proportions. So your book shows you one method to do that. In that method, we're going to use an approximation for the binomial distribution. So we're going to use the normal distribution as an approximation for the binomial distribution. So in your book, you can see that the population proportion is just a parameter, and we're going to get or collect a sample, one single sample, and the sample size is going to be n, and the number of individuals in the sample who satisfy a certain category is going to be x. So the proportion of the sample p hat is going to be x over n. So you have here on page 390 the steps to build a confidence interval for a proportion by using the normal approximation. So first, the conditions that should be satisfied to be able to use the normal approximation are that first, that we have a simple random sample, then that the population is at least 20 times as large as the sample. The number 3 is going to be that the items in the population are divided into categories. So that's the reason we needed to use a binomial distribution if we wanted to do the things exactly. And then number 4, the sample must contain at least 10 individuals in each category. So, and then once you satisfy those conditions, then there are 5 steps here to follow in order for us to build the confidence interval. At the end of the day, what we're going to do is we're going to compute the margin of error. In that way, the point estimate, which is p hat, plus or minus the margin of error, is going to give you the confidence interval. So the margin of error, you can see here, is going to be based on the z-score that is obtained by using the standard normal distribution. You're going to multiply that z-score by the square root of p hat times 1 minus p hat over n. So in that way, the confidence interval, you're going to have the lower limit is going to be this quantity. I'm going to increase a little bit the size of the font for you to see. So this is the lower limit or the lower bound of the interval, of the confidence interval. So it's p hat minus this product, the z-score, and the square root of these quantities. And the upper limit is going to be just p hat plus the margin of error again, which is the z-score times the square root of these quantities. However, we're going to use a slightly different method in our case. It's going to be a method that we're going to use in any case, regardless the size of the sample, because you're going to see later in this chapter that if you have small samples, you cannot use this method. This method is not applicable. So this method is applicable only if you have a large sample. What is a large sample? Then you need to follow these conditions to say that you have a large sample. So the method that we're going to use is going to be a method that's going to allow you to find the confidence interval for either a large or a small sample. Your book also shows you another way to get the confidence interval if you are dealing with a small sample. So let me show you the method. I'm just summarizes. I just summarize here the steps. So first, just remember, we are working with a population. The population has a parameter p, and we want to know about this parameter. We don't know anything, but we want to know. So the only way to know about this parameter is getting a sample from this population. And once you have the sample, you're going to need to compute the proportion of this sample. The proportion, again, is going to be just the number of successes, x. So this is going to give you the number of successes, and n is the number of trials. So once you have that, you're going to be able to find the proportion of the sample, which is p hat. So p hat is going to be a point estimate for p, but it's not sufficient. So it's very hard to say that the p hat value that you're going to find is going to be pretty close or pretty far of the actual value of p. So the only way to deal with that is getting an interval. So when you get an interval, you are gonna set a minimum value for your parameter and a maximum value for your parameter, and those minimum and maximum values are going to be determined by the confidence level that you want to have on that interval. So an interval for p is going to be required then, not just the point estimate. We need the interval. The interval is what is the most important part. The point estimate is just part of the problem. It's part of the solution. So, and we want that interval to have a certain confidence interval that is indicated by the percentage that you're gonna have the confidence level. So, the most important quantity then to find the interval is alpha, because alpha is based on the confidence level. So if you don't determine the confidence level, then you are not going to be able to find any interval. So you need the confidence level, you divide the confidence level by 100 and you subtract that value from 1, and that is going to be alpha. Then we only need to find the lower limit and the upper limit. So again, if you want to use the approximation, the normal approximation, just look at page 390 for the normal approximation. Here we're going to use a different approach. So we're going to find the lower limit and the upper limit by using the beta distribution. The beta distribution is going to give us the chance to get an exact lower limit and an exact upper limit for our confidence interval. So you have here the formulas. The lower limit is going to be 1 minus q beta. The parameters or the values that you need to enter for this function to work are 1 minus alpha over 2, comma, n minus x plus 1, comma, x. And then for the upper limit, we're going to use 1 minus q beta, and we're going to enter alpha over 2, comma, n minus x, comma, and x plus 1. So n minus x plus 1 or n minus x, so the value that is in the middle of this set is just a parameter that is known as alpha. This is another alpha, and this is a parameter beta, and this is another beta. So these alpha and beta are for the beta distribution. So you just follow this formula, and then you're going to be able to find the lower and the upper limits for your problem. So we're going to start with an example. We're going to work on example 8.14. So example 8.14 is on page 390. So that example says the following. In a survey of 800 parents, 632 said that the music education has a positive effect on academic performance. So first, we're going to construct a 95% confidence interval for the proportion of parents who believe that music education has a positive effect. Then we're going to answer the second question, which is about a claim that a music teacher has, which is that 80% of parents believe that music education has a positive effect. So we're going to see whether the confidence interval contradicts or not this claim. How? The only thing that you need to check is that the 80%, the claim of the music teacher, falls within the interval. If the 0.80 value for proportion is within the interval, then the claim is supported by the confidence interval. Otherwise, it's contradicting. It's contradicted by the confidence interval. So we're going to solve this problem now. So I'm just wrote the problem here for your notes. So that's example 8.14. So we're going to have here the number of trials, that's n, 800 parents, and the number of successes, x equals 6.32. So that's the first information that we need to obtain for our problem. So we have a sample where we obtain 632 parents believing in the effects of music education out of 800 parents. So this sample then has a proportion. So the proportion is going to be just x over n. So it's going to be x over n. So it's 632 over 800. So we're going to do this operation. So you can use your calculator, or you can use R. You're going to find that the proportion of this sample is 0.79. So, but what are the limits for the proportion of the population? We're going to use this value, we're going to use alpha, and in that way we're going to be able to find the confidence interval. So we're going to start with the confidence level, which is 95%. That's the confidence level. So from here we're going to find alpha. Alpha is just 1 minus the confidence level over 100. So this is going to be 1 minus 95 over 100. So we're going to find alpha equals 0.05. So that's the value for alpha. Now we're going to write the lower limit is going to be just 1 minus q beta, and we're going to enter 1 minus alpha over 2 n minus x plus 1 and x. So that's what we need for the lower limit. So we're going to enter the value. So it's going to be 1 minus 0.05 over 2, n is 800 minus x 632 plus 1 comma x is 632. So we're going to get in this way the lower limit for our interval in a minute. So then the upper limit. The upper limit is going to be 1 minus q beta. And now we're going to have alpha over 2 n minus x and x plus 1. So this is going to be 1 minus q beta 0.05 over 2 comma n is 800 minus 632 comma 632 plus 1. So this is going to be the computations to get the lower and the upper limit. So let's go and start working with our console and find the results. So 1 minus q beta beta. We're gonna write here 1 minus 0.05 over 2 comma 800 minus 632 plus 1 comma 632. So this is the information for the lower limit. So now the information for the upper limit is going to be 1 minus q beta, and then we're going to have 0.05 over 2 comma 800 minus 632 comma 632 plus 1. So that's the upper limit. So now we're going to write this information in our notes. So I have the lower limit 0.76, 0.10, 62, and 0.81 is the upper limit, is 77,385. So now we're going to be able to write the confidence interval for the proportion of this population. So we're going to write that the 95% confidence interval for this population is going to be 0.760162 less than p less than 0.8177,385. So that is going to be the answer for the lower and the upper bounds for this problem, for the proportion of this population. Now we're gonna go to page 392. In that page Now we're gonna use a method to find the size of the sample. So sometimes when you're gonna conduct a research, you want to know what is gonna be the size of the sample that is gonna give you a certain margin of error. So we're gonna use the formula that is on page 392. So to find the sample size n. So the formula is just n is going to be equal to p hat times 1 minus p hat times z alpha over 2 over m. And this is going to be square. And what is m? M is the margin of error that we want for our confidence interval. And what is z alpha over 2? It's just the z-score, that's the critical value or the z-score corresponding to corresponding to alpha over 2. So it's going to be related to the confidence level. Now, if p hat is not known, then you're going to set p hat equals 0.5. That's the worst case scenario. Okay, so this is the information that we're going to use. Now we're going to solve a problem, a couple of problems. So we're going to solve now example 8.15, which is on page 393. So we have here example 8.15. So in this example, they say example 8.14 describe a sample of 800 parents, 632 of whom believe that music education has a positive effect on academic performance. Estimate the sample size needed so that a 95% confidence interval will have a margin of error of 0.025. So we want to know how many people do we need to survey, how many people we need to survey to get a margin of error of 0.025. So let's write this down. So we have example 8.15 on page 393. So here we're going to use, so we know that n equals 800, we know that x equals 632, so we know a proportion, so the proportion is again 632 over 800, so this is 0.79. So we are using this proportion from a previous sampling to estimate the number of people that we need to interview, the number of parents that we need to interview to get a margin of error. In this case, the margin of error that we want is 0.05, 0.025. And also, we want a 95% confidence level, meaning then that we're going to have alpha equals 0.05. So first we need to find the corresponding z-score for this alpha. So remember, when you are using this formula is based on the normal approximation. So this is by using the normal approximation, to the binomial. to the binomial distribution. So we are using the normal approximation to the binomial distribution. So with this value of alpha, we're going to be able to find z alpha over 2 by using q norm 1 minus alpha over 2. So this is going to be q norm of 1 minus 0.05 over 2. So we can use R to find this value. The value is going to be just 1.959964. Okay, so now we're going to use the formula to find the size of the sample. So the formula requires p hat 1 minus p hat and z alpha over 2 over m square. So we already have this information, so this is going to be equal to p hat is 0.79 times 1 minus 0.79 times z alpha over 2, 1.959964 over m. The margin of error that we want is 0.025. Remember, the margin of error is the difference between the upper limit and the point estimate, or the difference between the point estimate and the lower limit. And we're going to square this. So let's use our R console to find the answer for this computation. So let's go and check our R console. So we have 0.79 times 1 minus 0.79 times parentheses 1.959964 over 0.025, and we're going to square this last fraction. So we're going to get n equals 10, 19.677. So the value for n, and then we're going to need to use for our research, for our survey, is just 10-20 people, 10-20 parents are going to be interviewed. Okay, let's run one more problem by using the same formula. So now we're going to solve example 8.16. This example is about the same kind of problem. We plan to sample parents in order to construct a 95% confidence interval for the proportion who believe that physical education has a positive effect on academic performance. We don't have a value for p hat available, so we're going to estimate the sample size needed. So that 95% confidence interval will have a margin of error of 0.025. So this is a problem where you don't have prior information on the population. So in that way, we don't know the value for p hat. So p hat is unknown from previous research. So we know that n equals 800 again, that x equals 632. This is the information that we had for a previous problem. In this case, this information don't work for us because this is for music education and we are working on a problem on a physical education. So since we don't have value for p hat, we're going to set p hat equals 0.50. So, and the rest is going to be the same. So we're going to start with a 95% confidence level. that you can transform into a value of alpha equals 0.05. Then we're going to find the corresponding z alpha over 2 again by using Q norm. So the value just that we found for the previous problem is just 1.959964. So what is the difference now? That we're going to use p hat equals 0.50. So our formula is going to be the same formula, but with a different value for p hat. So we're going to have p hat 0.50 times 0.50 times 1.959964 over 0.025 square. So let's see now what is the value for our sample. In this case, without prior information, you're going to see that the sample should be increased to get the same certainty. So we're going to use the previous computation. The only thing that we're going to modify is that instead of 79 is 50 and also 50 here. So now we need more people. We need the answer is 1536.584, but we cannot interview a fraction of a person. So we need to interview 1537 parents to know about their beliefs on physical education, on academic performance. So we're going to finish now with this section with computing confidence intervals for population proportion when we have only small samples. So you're going to see here in your book on page 395 that they are going to suggest a method for constructing confidence intervals with small samples. So there is a method here, so you're going to need to do a lot of things to be able to get the confidence interval. We're going to just use the same formula that we used for the first problem when we started this section. So I'm just going to show you example 8.18. So now that's the example that we're going to solve. So it says that in a random sample of 10 businesses in a certain city, 6 of them had more than 15 employees. Use a small sample method to construct a 95% confidence interval for the proportion of businesses in this city that have more than 15 employees. So this is our problem. So this is to compute the confidence interval for a population proportion, with small samples. So example 8.18 on page 395 is telling us that there is a sample size of 10 businesses, and out of these 10 businesses there are 6 businesses with more than 15 employees. So there are 10 businesses and there are 6 businesses with more than 15 employees. So again, we want a confidence level of 95%. So this is going to give us an alpha value of 0.05. So let's use this information. We're going to have the lower limit is going to be just 1 minus q beta or 1 minus alpha over 2 comma n minus x plus 1 comma x. So in this case is 1 minus q beta, 1 minus 0.05 over 2 comma n is 10 minus 6 plus 1 comma x is 6, and that is going to be the lower limit. Now the upper limit, we're going to compute the upper limit with the same formula that we used before. It's going to be 1 minus q beta alpha over 2 n minus x, x plus 1, and the values that we're going to use are 0.05 over 2 comma 10 minus 6 and 6 plus 1. So this is going to be to get the upper limit. So let's put this information into our R console and let's see what happens. So we have 1 minus q beta of 1 minus 0.05 over 2 comma 10 minus 6 plus 1 comma 6, and then we have the next one is going to be 1 minus q beta of 0.05 over 2 comma 10 minus 6 and 6 plus 1. So we have our two values here. So the lower limit is going to be 0.26, 23, 781, and the upper one is going to be 0.87, 84477. So then that means that the confidence interval for this proportion is going to be 0.26, 23, 781 less than p less than 0.87, 84, 477. So this is going to be our 95% confidence interval. So now you're going to have the chance to work on these problems by solving a couple of them from the exercise set. So you just go and check on section 8.3 on page 398. So from that exercise set, you're going to work two problems, problem 20 and problem 22. So I'm going to show you those problems now. So problem 20 and problem 22 are here. Okay, let's start with the first one. So problem 20 is here now. So it's about working at home. So take a screenshot of the problem. And then we're gonna work on problem 22. Another screenshot for this problem. internet service. We're going to continue now with section 8.4 to finish the lecture for today. So section 8.4 on page 401 is about confidence intervals for a standard deviation. So we're going to use another distribution for our sampling distribution. So that distribution is going to be the chi-square distribution. So you have here, for example, in your book on figure 8.13, different chi-square distribution. So the chi-square distribution is a distribution that is not symmetric with respect to the center. So to build the confidence interval, your book shows you the method on page 403. So you have here the formula to build that confidence interval for the variance and the confidence interval for the standard deviation. The only difference that the lower limit for the variance, you're going to take the square root of that to get the lower limit of the standard deviation, and the same thing with the upper limit. If you take the square root of the upper limit, then you're going to get the upper limit for the standard deviation. So this is very simple. The only thing with this information in your book is that the limits are reversed. So this should be the upper and this should be the lower limit. So when you are working the procedure, it's going to be the same thing. So what they say that is the lower bound actually is the upper bound, and this is going to be the lower bound. And you're going to see that when you get the values, you always write first the lowest, then less than, sigma square less than, and then the greatest value of the two that you're going to obtain. So at the end of the day, is irrelevant this notation, because you're going to see which value is the highest and which one is the smallest. So we're going to solve a problem. We're going to solve problem A.20. Problem A.20 is the one that we're going to solve now. So we're going to construct a confidence interval by using this data set. So there are here 7 values for compressive strengths of 7 concrete blocks in pounds per square inch. And we're going to assume that these values are a simple random sample from a normal population. And we're going to construct a 95% confidence interval for the population standard deviation sigma. So we're going to use a data set. Sometimes you're going to be given the standard deviation of the sample directly, so you don't need to compute the standard deviation of the sample or the variance. Sometimes you're going to be given the data set, so you need to process the data set in order for you to get the variance of the sample or the standard deviation of the sample. So this is then our notes. For our notes, we have section 8.4. We know that we have a population with parameters sigma squared, which is the variance. This is the variance of the population. This is the standard deviation of the population. And we're going to collect one sample with size n. And from that sample, we're going to compute the variance of the sample and the standard deviation of the sample. If you are given a data set. If you are given the values, then you just proceed and compute the values. So the first step is going to be always the same. We need to convert, to transform the confidence level that is required in percentage into an alpha value. Remember, alpha is the significance level, and it's always 1 minus the confidence level divided by 100. And then we have the formulas. So I'm just reversing the formulas that you have in your book on page 403. So you can check page 403. So we have a lower limit, you have an upper limit. You can see here this symbol chi-square, the symbol chi, and then the square here. So these are the values that now we need to get from tables, from your Texas Instrument 8384 calculator, or by using R. Once you get these values, obtain the result of these formulas, you're going to get the lower limit and the upper limit. If you want the confidence interval for the standard deviation, then you need to take the square root on everything. Using R, I'm just writing here these formulas expressed in the way that you're going to be able to use the chi-square distribution. So be aware that I'm writing here just variance, but you need to enter here a numerical value or a function that computes the variance, but don't write variance only because our console is going to tell you that something is wrong. So you either, if you have a data set, you're going to enter those values in the usual manner. So you're going to have x equals c, and then you enumerate all your values separated by commas, and then you're going to obtain the variance by using the function var over of x. So if you do that, you get the variance. So let's work on example then, the one that I just mentioned, 8.20. So that example is written here. So again, it's a data set. So we need first from the 95% confidence level, 95%, we're going to obtain alpha equals 0.05. So it's 1 minus 0.95, it's going to be 0.05. Then I need the variance, is not given, so I need to compute the variance. So I'm going to enter the data set. So I'm going to enter these values into R. And in that way, I'm going to be able to find the corresponding variance for the data set. So until we enter the last one, 7 values are going to be here. And then we're going to compute the variance. And then we're going to use that information to compute the lower and the upper limit. So let's go and use our console to find the solution for this problem. So x is going to be a list of 7 values. So 1989.9, 1993.8, 2074.5, 2070.5, 2070.9, 2033.6, and 1939.6. And check my computation. I can make mistakes. If I make mistakes, you can fix the problem at home. So then you can get the variance of this data set. So the variance is just 2699.865. So that's the variance for the data set. So now we're going to proceed and we're going to compute the lower and the upper limit. So let's start with the lower limit. Is I'm going to write the formulas first in your notes. So I have here the variance. So now the lower limit is going to be just n minus 1 is 7 minus 1 times the variance of x. So we can write this if you have the data set, or you enter directly the value here. Then over q chi-square of 1 minus 0.05 over 2, comma, n minus 1 is 7 minus 1. So this is going to be the lower limit. And the upper is going to be very similar. So 7 minus 1. Then the variance I'm going to use now 26.99A65. So this is when you only have the value that is provided in the word problem, then you just write the value directly. If you have a data set and enter the data set in this way, then you can write var of x. So q chi square, and then alpha over 2 is just 0.05 over 2, comma 7 minus 1. This is going to be the upper limit. So let's work on these two limits first to find the variance, and then in the last step we're going to find the standard deviation. So we're going to write then for the lower limit just 7 minus 1 times, I'm going to use variance of x because I enter a data set. Remember, if you enter a data set, you can do that. Then we're going to divide that by q chi square, and then 1 minus 0.05 over 2, 7 minus 1. So that should be the lower limit. So it's going to be 1121.1. That's the lower limit for the variance. Then we're going to repeat the computation, but now instead of using this formula, because assume that you were not given a data set, you were given directly the value of the variance, then you need to just type the value for the variance. And when you are computing the upper limit, you need to write 0.05 over 2. So that is going to be the upper limit, 13,091.9. So with that, we can construct now the confidence interval for the variance. So we're going to write here that the 95% confidence interval for the variance is going to be 1121.1 less than sigma squared less than 13,091.9. So that's the confidence level for the variance. Now, if we want the 95 confidence interval for the standard deviation, we need to take the square root of everything. So if we take the square root of everything, we're going to get the confidence interval for the standard deviation. So we're going to get this value. So how do you do this in R? You're going to type square root of 1121.1, and here is square root of 13,091.9. So let's see what values we get by taking the square root on both sides. Or you can use your calculator too. So I'm going to use square root of 1121.1 and square root of 13,091.9. So those are now, one is the lower limit for the standard deviation, and the other one is the upper limit for the standard deviation. So, and with that, we're going to finish this chapter. I'm just going to give you the assignment to complete your classwork. So I have here now the 95% confidence interval for the standard deviation. So in the problems in your quiz and in the exam, this is what I want to see. So the intervals, if you are asked to estimate the standard deviation of the population, when they say estimate the standard deviation of the population, they are talking about an interval. They are not talking about a single point. So to finish this, you're going to work on section 8.4, exercise set, on page 405. I'm just going to give you one problem. We're on problem 15, and that is going to be all for this section and also for this chapter. So let's see. It would be good if you work also a problem where you are given directly the standard deviation. So you're going to work problem 14 and 15. So in one case, 15, you're going to get a data set, so you do what I did, enter the data set. In the other one, you're going to get directly the standard deviation, so you just substitute the value on your formula. So I have here 14 and 15. So 14, you have scores on IQ tests are normally distributed. A sample of 25 IQ scores has a standard deviation S equals 8. So they are giving you the standard deviation. Remember, if you need the variance, you're going to square this value. The variance is going to be 64. So you're going to construct a 95% confidence interval for the population standard deviation. And then we have problem 15, baby weights. So now you're given a data set. You're going to assume that the population is normally distributed. So you need to enter the data set first into R and compute standard deviation or the variance. Even though they say that you're going to construct the confidence interval for the standard deviation, it would be good for you that you start constructing the confidence interval for the variance first, and then you take the square root of everything and you get the confidence interval for the standard deviation.